Following our threading tutorials, let's do something fun. Loggers are one of the basic entities in our industry. There are a ton of logging libraries out there, but let's make our own just to see how to deal with a multi-threaded I/O. Note, this video might contain some cuts to limit typing I am going to make, just to keep it a bit shorter. First, let's make a simple logger skeleton. That's our simple skeleton, doesn't contain much, simply a non-copyable class. Now, what would be the requirements for our logger? It should work like a typical C++ stream. It should be thread safe, naturally, and messages from different threads should not be mixed together. As the first step, let's create our simple stream-like API. First, something to log, let's call them normal values. Just to the standard output for now. We also need to make overloads for things called I/O manipulators. These are pretty straightforward. Let me put them in there. I don't want to get into the details what they mean specifically, but they in short manipulate the output of our stream. Okay, let's make a simple test and see if it works. Here's our log instance, and let's log, for example, ABC. Let's log a number, 32, and end with the end line. Cool. So, does it work? Of course it does. Okay, so that pretty much takes care of the first requirements, having a stream-like API. For starters, we are simply forwarding all past values and I/O manipulators to the default output. So let's go a step further. Let's introduce a logging thread. We will use a simple queue of functors which will then log values. The idea behind using functors to logging values is that a functor, specifically a lambda, can capture an arbitrary value and can be easily stored, then easily invoked. We will also use a condition variable to notify our logging thread of new elements, just like we did in our thread pool example. Small note: when we create a functor with the value moved inside, which will be then output to the log, we require the type of this value to be movable or at least copyable. For the purposes of this simple example, that's not an issue. Let's first introduce our list of functors. Why a list? This will become apparent later. We also need our mutex to guard this list and use it with our condition variable. And the condition variable itself. Typo. We also need a simple flag to notify our thread that we're shutting down, which is false by default. We will need our logging function. Let's call it serialize. This will be run in our logging thread. And of course we need the thread itself. Let's make it here, std thread. And let's point it to our serialize. Method. Let's not forget about actually setting the variable for closing. There was no destructor here. Okay. We are making one. we are locking our mutex to set the closing flag. End of critical section. And now we will notify our logging thread that something happened. In our case, close intent. 1. And now we can wait for our thread to finish whatever it's doing. What about the thread itself? We will use a simple while loop, if I can write it without typos. As usual with condition variables, we need the unique lock. We will wait on our notification variable until we are either closing or there's something to actually log. So we are using wait by passing the lock. And here we are using a simple predicate which will tell us when something happened. Visual Studio isn't the greatest in code completion. Okay, we'll manage. Empty. So now it sees log queue. Great. Alright, so at this point we are either closing or we have something in our log queue. So let's output anything that's waiting to be logged. Simply call our logging functor. We will see in a minute what it does. Clear queue. And if we are closing, let's jump out. Cool. So what we need to do now is put something in our log queue. Let's make a helper method for that. Right. This method will once again lock our mutex because we are trying to insert something to our queue, so we need to protect it. Lock queue and place back, and here's where the magic happens. Forgot the actual value. Our value is moved inside the lambda, and Visual Studio did something strange there. And inside we will simply print it out, just like we did before. Now all that's left to do is notify our thread that we have a new element in the queue. So again, notification variable, notify our one thread, return this. And now let's simply call it everywhere. As usual, let's check if it works. And voila, it works. Now we have a very functional skeleton. We are starting to log values in a separate thread, so the main one is free to do real work. If we left it like that, logged values from other threads would be intermixed. We need one more step, the last requirement. Log values for a given thread as long as it's appropriate, example when a new line is encountered, and then a log from another thread. To detect a new line, technically it's called a sync, we need to implement our own stream buffer, which will react to sync commands like std endline. For simplicity, we will use a string buffer as the base for our own sync detection buffer. And here it is, in its all simplicity. We have our log buffer, which is based on standard string buffer, and all it does is override the sync method. Right now it doesn't do much, but we'll get to it later. To use that buffer, we actually need to associate it with a stream. And here it is, a very simple implementation of an output stream. All it does is pass our own log buffer to the base OStream class. Then it can be used like a standard output stream, and our values will be logged into the string buffer. One more thing we need to change is to substitute this cout for our stream. So we will make our log stream here, so we can capture this, and now we are simply outputting our values to our stream. If we run this now, nothing will be shown, right? That's because we are simply logging into a string buffer and we're not doing anything with it yet. Okay, so now we're logging to our custom stream, which is backed up by a string buffer and can react to sync commands. Good, but what we actually should do with them? We should log the data until we encounter a sync. This means we need to store information about the thread the data comes from. After a sync comes, we should flush our buffer containing our logged values and start logging data from another thread, if one exists. In order to do that, we need to remember from which thread a given piece of data comes, which means we no longer can simply store a list of functors. We also need to store a thread ID associated with each value. So let's make a simple struct called log entry, which will contain a thread ID and the functor we used previously. It's called functor. Not very creative, but it does the job. And now we are simply keeping a list of log entries. To monitor where are we within this list, which thread we are actually logging data for, we need two more pieces of information. First, we will use an iterator to the log queue, which will point to our current element. I could have used an alias for the whole list, but whatever. Decal type does the job. Current log is to the end. We wanted to point to the end of our log queue initially, and we also need some information about for which thread we are currently logging values. So current thread ID. Okay, so we have all this information. Since we want to react to syncs, or let's call it flushes, because we want to flush the output when a sync comes, we somehow need to inform our logging thread that such event took place. So let's introduce a flag called flush equals false. This will tell us that the last operation resulted in a sync and we should flush the output. We would also like a method which will actually set flushed to true. So let's call it handle sync, because it will handle our sync commands and it will set this flag to true. Okay, and we want to call handle sync from our log buffer here, because the buffer in this overridden method can react to sync commands. So we need to pass on the log itself into the stream and later into the buffer. Here we're simply storing our log, and in sync we are calling handle sync from the log itself. We also need to pass the log from our stream into the buffer. Done. Well, almost done. Now it's done. Alright, so now we obviously need to modify our logging thread somehow. First, we need to get rid of this because we are not interested anymore if the log queue is empty or not. We are interested in knowing that our current log pointer, in our case the pointer being an iterator, actually points to an end or not. Because if not, this means we potentially have some more data to log. In here we need to get rid of this all and implement some more advanced logic. First, let's handle closing. So if we are closing, well, we obviously need to do something and then break out. We would very much like to output all of the values which are in our log queue, but we also want to keep our requirements, so we don't want to intermix any values coming from different threads. So let's make a loop while our log queue is not empty. We need to do something. First, let's check if our current log pointer, again, this pointer being an iterator, not a, well, memory pointer, if it points to the end of our log queue, that means that we have moved through all of the values for our current thread. By current thread, I mean the thread we are currently logging the data for, and we need to start all over from the beginning of the log queue. So we are simply rewinding the log queue to the beginning. We're running our current log to the beginning of the log queue, sorry. We know it's not empty, and we are setting our current thread ID to the new thread we are logging the data for. So at this point here, we know that our current log pointer points to some data, to some, well, log entry, and our current thread ID points to some thread we are currently logging the data for. Okay, so let's go through the list and output everything for our current thread. So once again, while current log isn't the end of our log queue, let's check if our current thread ID is actually the same as our current log, because our list contains intermixed entries and we need to output them in order. So if this is the same thread, then as before, let's call the functor. And after that, let's remove the entry from the queue. And here you can see why we're using a list. So we can very efficiently remove elements from an arbitrary position. Let's go further. If our current log belongs to a thread another than our currently logged for thread, then let's simply skip this element. And at this point, we have called all our functors, well, at this point, all our functors in order, so our log buffer contains data logged for each thread without any mixed entries. Now we simply need to output it somewhere. First, let's introduce a method which will return the contents of our log buffer, and also it will clear the contents. Let's go like that. Let's reset the contents. Okay. Now let's introduce a method which will simply output the data. Let's call it flush cout get string and clear, and after that it should set our flush flag to false, and let's call it here. The flush method will also be called in a minute outside the closing condition. That's why we are resetting the flushed flag. Here we can do something similar to the above, but a bit different. Let's introduce a do loop. At this point we know that there is at least one entry in our log queue and our current log points at it, so we can use do while instead of simple while. Whoa, let's venture to completion. And here, let's check if we have something more to log. And also, if we are still working on a given thread. Inside, we can simply call our functor, just like above, and check if we have the flushed flag set, which happens when a sync is encountered. We flush the output, then we erase current logged element, and as here we rewind the current log to the beginning of the queue. But if at this point our current log points to the end of the queue, which means that the queue is empty, we simply reset our current thread ID to an empty one and we break out. Otherwise, we set our current thread to our currently logged thread. So what this does in practice, if we flushed the output, we simply remove the current element because we're not interested in it anymore. We rewind our log to the beginning. If the log queue is empty at this point, we pretty much reset all our internal state, and we otherwise assign new thread ID to the thread coming from our current log. At this point, we switch our thread to another one, and we simply start outputting its logged values again until we encounter a flush or we are closing. If we have not encountered a flush, well, a sync, then we need to move our current log pointer to the next piece of data, the next log entry for our currently logged for thread. So we will use find if as the beginning. We will use the next element after the current one because we need to erase the current one since we logged it a second ago to the end of log queue. And here we have our predicate. This will be our logged entry, right? And here we return true if current thread ID equals the thread ID from the inspected entry. These three lines basically search for the next entry for our given current thread. And that's it. This do loop will output all stored values for a given thread and switch to a new one if needed. We also need to modify the write method, since we are no longer simply storing functors, but also thread IDs. So we will get the ID of the current thread, get ID, we emplace the whole element, and we need to add some logic here. If our current thread ID is empty, which basically is the case when the logging starts, we assign the initial values to our internal state. So this points to our first element. Our current thread ID then becomes our first thread ID we have, and we are notifying that something happened. Otherwise, if our currently logged for thread equals our current thread, then we can simply notify that we have a new entry. Why aren't we notifying for every thread? Well, because we know that if our current thread is different than our currently logged for thread, then we won't output anything at all. So there's no point in notifying our serialize method that something happened. Here we also need to do one more check, because our current log might point to the end of the list. So we simply need to point it to the element just before the last. So we have something to actually log. Okay, time to see if it actually works. To do it, let's introduce some threads here. Let's call it T1. This thread will output what? Will output, for example, T1 and end with an end line, which is consider a sync command, which will flash our values. And let's introduce another thread, maybe here, because why not, which will output T2. Then we of course need to join them both. And let's see what happens. Okay, take a look at that. We logged data for our first thread. We logged 2 pieces of data for another thread. And then we logged a third piece of data for a third thread. Note that none of this is intermixed. We can add more elements to further visualize it. Let's call it T1, 1. Let's call it T1, 2, 2, and end with another. And whoa, what's that? End line. Let's do the same here. Of course, this and 3 and 4. And let's launch this and see what happens. And look at that. We have 2 pieces of data logged for our main thread. Then we have 2 pieces of data logged for our T1 thread. Then we have an end line. Then we have another 2 pieces of data logged for our first thread and an end line. And the same for the third thread. Note that nothing here gets intermixed between threads. If we're lucky, we can try to run it again. We see something changed. We can see that our main thread jumped between the 4 pieces of data we output from the first thread. And notice that it's not intermixed. We are logging here with a new line, which makes our logger jump to our new thread and log the data, which again ends with a new line, and then it jumps back to another thread, etc., etc., until an end line, or like I said before, a sync, is encountered. Now thread values will be intermixed with each other. You can freely use this one log instance in multiple threads and nothing bad will happen. So I hope you found this interesting. I hope you found this informative. It was a bit long, but I hope you now see that multi-threaded I/O is not that hard, but you need to be certain of certain aspects, like intermixing data between threads. If you have questions, post them below. If you like it, click subscribe, and I'll see you in the next one.